Hi everyone. In a previous code along, we talked about how to find frequently occurring words in a short text. In this installment of Programming for Lovers, we will zoom out and solve the problem of which strings occur as clumps, occurring frequently in short regions of a long string like a genome. We will then apply our solution to the E. coli genome to find out how many strings occur surprisingly frequently in short regions of that genome and that may serve as hidden messages to the cell. Stay tuned, because I think that the answer is really going to surprise you. If you enjoy what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. To get started, you'll notice that I've created a folder called Clumps in our Go src source code directory, and then I've got a file called main.go within that directory. I've also got a little bit more starter code than I normally have. So here I've got a function called frequency table, which, hey, that's something that we wrote in the previous code along. What does it do? It takes a string text and an integer k as input, and it produces this map whose keys are the substrings that you see in that text having length k, and whose values are, for a given substring, the number of times that that substring occurs in the text. So we're going to use that function to our benefit when I solve a more general problem, which is the frequency table might be useful if I know, say, a region of a genome where I'm looking for frequent words occurring within that region. But what I might be interested in zooming out more globally is to scan over an entire genome, and then over that genome, figure out where are the regions where I see frequently occurring words. So over the entire genome, where are places where I see clumps of strings? And I can be a little bit more precise in terms of how I define that. And I'm going to do so by starting to write the comment for the function that I'm going to use called FindClumps. And it's going to take as input a string text and some integers. So the integers are going to be k, l, and t. What it will return is a slice of all the strings that we find that occur frequently in short regions, what I'm calling clumps here. So a slice of strings representing all substrings of length k, so k is still the length of a substring, that appear frequently, meaning at least t times, in a window of length l in the string. So they must occur frequently in a short region, and how I'm going to define short is I'm going to have some parameter L that's going to be probably much shorter than the length of the text, and then that window of length L is where I have to look for this particular substring of length K to be frequent. So I know that the first line of my function is going to be called FindClumps. We take a text, we take integers K, L, and T, and I'm going to return a slice of strings. And because I'm going to return a slice of strings and I don't know in advance how many strings I'm going to find, I'm going to say, let's set pattern equal to make a slice of strings having length 0. And then way down here at the end, that's what I'm going to return. Another parameter I'm going to need to know is the length of the text. So let's set n equal to that length. And then it's just a matter of ranging over all possible windows. And this is something that we've done now in several code alongs within this chapter. I said when I introduced it, we would have this pop up. This is something that we kind of stamp on the brain of every computational biologist out there, which is that in a string of length n, if you're looking for substrings of length, say k, there are n minus k plus 1 total such substrings. And here I want to range over all possible windows, but the windows have length L. And so I know that I'm ranging over all possible length L substrings of text. So I'm just replacing k with L in my formula, and I know that I'm going to be ranging over all possible starting positions. So I is going to range between 0 and going up to, but not including, n minus L plus 1, so that I'll have n minus L plus 1 total starting positions, ranging between 0 and n minus L inclusively. And as I do that ranging over the starting positions, each time I need to set the current window. And the current window that I'm interested in is the substring having length L that starts at position I. We already know from working in this chapter what the notation for that is in Go. So we would say the current window is equal to the substring of text starting at position I, going up to, but not including position I plus L, since when you subtract that top index from the bottom index, it's always going to be the length of your substring that you're interested in. The idea here is that L is bigger than K, so then within that window, we're looking for frequently occurring substrings of length K. So if we're looking for frequently occurring substrings, let's make the frequency table for this window. So within that particular window, I'm going to go through and figure out how many times does each substring of length K occur within that window. I can do that just by calling this frequency table subroutine that we have. So I will set frequency map is equal to the frequency table. And it's tempting to give it text since I've written that as the input before for frequency table. But what we're really producing is the frequency table for that window given this parameter K that's going to tell us the length of the substrings that we're interested in. Now I've got the frequency table, the subroutine has helped me. Now it's just a matter of ranging over that frequency map and saying what occurs frequently. Well, what occurs, i.e., T or more times. So to figure that out, I've already generated the frequency table, so I can range. I can say, well, let's range over all possible, say, patterns or strings S that are keys of my frequency map. So I know how to range over the keys of the frequency map. And here's where I want to say, append each of these strings to my growing patterns if, well, one of two things, or two things have to occur. If S occurs frequently and S doesn't already appear in the patterns. So there's no point in appending all these duplicates. So if I've already found S, it occurred frequently in one window, probably if I shift that window over, like one symbol, probably S is going to be frequent in that window too. So I don't want to keep appending the same string over and over again. Instead, I'm just going to append it once. So I need an if statement, and this is going to be a way of practicing our Boolean logic here. I need two things to occur. I need frequency map of S to be greater than or equal to T. And notice I'm using frequency map of S, so as soon as I use that, I'm probably just going to have value, or I guess call it number of occurrences. So if the value associated with S is greater than or equal to T, and I want to make sure that I don't already see S within that slice of strings patterns. So I might use this as, say, use a subroutine to help me here, where I'll say, is it the case that S appears in patterns? Does this slice contain the string S? And I only want to append S to the patterns if that is false. So if that is not the case, it does not appear. In this particular case, that is where I will append to patterns my current string S. And if we're getting tighter in terms of our code, every time you have something equal to false, you can just replace that by saying not equal to, or not, excuse me. And that's our function. Of course, I need to write my contains subroutine, but that's going to be a much shorter function. And this is hopefully, as we get more and more comfortable with ranging over, say, slices, this type of function should be this sort of thing that will start feeling more and more comfortable. So I can write this function by saying contains is going to take as input, well, a slice of strings and a single string. What does it return? Well, it returns true if S is contained in the slice and false otherwise. So we'll have func contains, let's say, patterns as a slice of strings, S as a string, and it's going to return true or false, so we know it's going to be returning a Boolean value. And then it's just a matter of ranging over all of these patterns that we see. So this is a slice of patterns. I'm not interested in the indices. There was nothing interesting about the indices. So what I will do is I will range over the values. So here the value is a string. I can make this called pattern if I like. And we'll range over the patterns. And here I'm simply checking, is it the case that pattern is equal to our string S that we're interested in? And if I ever find such a match, then I know that I have found that, and I know that S is contained in the patterns. So at this moment in time, I can flip the light on and exit the function. In other words, I can just return true. And then the idea, and we've seen this sort of function previously, once we survive all of these ranges over the entire slice, if I don't find any such matches and I make it through that for loop, then I can conclude the default is to say I didn't find anything and return false. And that's our contains function. I like that function. It's a nice, clean function. It's good practice. I wrote it for that reason. Also, at the same time, I don't need this function. So I keep it here for a reason, but I'm also not going to need to call a subroutine here. I'm going to do something just a little bit more clever in terms of ensuring whether or not I have seen this string S before in my collection patterns. What I'm going to do is keep track of this as I go. So rather than kind of maintaining this as a slice, what I'm going to do is I'm going to maintain a map that's going to essentially contain the information, have I seen this string, have I added this string to patterns yet? So the way that I'm going to do that is when I declare my pattern slice, I'm also going to declare a map. And that map is going to be called found patterns. And it's going to be a map of strings to Boolean values. And this will track whether I have added a string to patterns yet. Okay. And then as I go, what I'm going to do is check, is it the case that I have seen this pattern S within my found patterns map? And so here, rather than use my subroutine contains, I'm going to check, is found of patterns S equal to false? And that's going to be okay. So imagine that I haven't seen this string S yet. We know from a previous code along that Go, if it tries to access found patterns of S and S is not a key of the map, it will give us the default value associated with whatever the values are in that map. In this particular case, the values in the map are Booleans. So if S has not occurred as a key in that map, then found patterns of S is going to evaluate to false. I'm actually not going to shorten this. I'm going to leave it as equal to false because I think that's a little bit more instructive. So if found of patterns S is equal to false, that means that we essentially haven't seen it yet. And once I append that string to my growing slice patterns, here is where I need to say, now I've found it. So now I'm going to actually have an entry for S in that found patterns map and set it equal to true. And in this way, I'm not going to need a contain subroutine, and this map is just going to store that information that I need as we go. We'd like to apply our FindClumps algorithm that we've written here, which is doing something I think reasonably sophisticated without a huge amount of code, to a real genome. The first thing that I might do, though, is apply it to, say, a smaller example. So I could save this, and let me make sure that everything compiles first. So I've got a terminal here. It's open to the Go directory. I'm going to cd into src clumps. Then I'm going to compile with go build. That took a while, but it worked. And then I'm going to, I could run this if I like, with either clumps.exe on a Windows machine or /clumps on a Mac, and all that's going to happen is this print statement. So instead, let's set some things. Let me set, say, a text is equal to AAAA, and then a bunch of stuff, CG, TCG, and then some A's. And I could set K equal to 2, and L equal to 4, and T equal to 2. So here I'm looking for strings of length K that occur in windows of length 4 at least 2 times. And there's only one such string. I've kind of given a very simple example here where the only string that's going to occur as such a clump is AA. But we can make sure that we don't see AA more than once. So I could call find clumps on this text K, L, and T, and print out the result, and all I should see is one string get printed here, which is AA. So I've saved that. I'm going to up arrow twice to go build and up arrow twice again to run this, and that's what I see. I see only AA. Of course, that's boring. And I'm going to delete this entirely. And instead, I want to plug in a real genome here. But if I start copying over a genome with millions of nucleotides, things are going to get weird quickly. And so instead, a much stronger thing to do rather than clutter my text editor here is instead let's just read this from a file. And one of the things that we might do is acknowledge that this genome file is just out there on the internet. And that gives us an opportunity to show you how to read in a file from a URL, which is what we're going to do. And we're going to need to expand the collection of package imports that we have to a few things. So currently we're just importing FMT. We're also going to need to import net/HTTP. This is for accessing URLs. So I have some built-in code from that, which is good. And we're also going to need IO, which is needed to read and write. I should say read from and write to files. So when we actually need to read out the file that we grab from the internet. And then we also need a log, and this would be in case of any errors. So this is needed for log files. All right. So we need those three packages. And now I'm going to go into main, and I'm going to grab the URL that I'm interested in. A URL is just going to be a string. And so the first thing that I will do is set the URL equal to the string that I'm interested in, which in this particular case, we've got the E. coli genome stored at another educational project that I'm involved in called Bioinformatics Algorithms. And so I'm just going to grab from the URL there. This is, of course, a string, so I need to give it the string double quotes. So this is at https://bioinformatics-algorithms.com/data/real-dataSets/replication/e coli.txt. Hopefully I typed that out right. And then we want to first access that URL. And we're going to access that URL. It's going to give us what's called a response object. And we'll talk more about objects later in the course. But for now, I'm going to be able to check whether or not that request was good or not. And so there's going to be an error associated with it too. So I'm going to have a response variable called RESP and then an error. And I'm going to use the built-in function http.get and give it the URL string that we're interested in. And then I'm going to say, was there a problem? So if the error is not nil, then I'm going to panic and print the associated error message to the console. We next need to make sure that if we make it here, then the response was okay. And let's check that there's kind of a normal status code associated with the website. So we're going to do this with accessing a field of this response variable called status code. So we have if resp.statuscode is not equal to what is called the OK status, which the website will tell us is 200 typically if everything is okay. And if that's not equal to 200, I want to log this and print an error message. So I would say received non-OK status, and then %v for formatting, and then give it the response status. Okay. If we make it here, all has gone well, and we're ready to read in the file. I should say also, if you would like to, go ahead and visit this URL, and you know what you're going to see? A boatload of ACs, Gs, and Ts. So you can take my word for it, or you can visit that URL if you like. It's going to not be tremendously surprising. But I also find that There's something nice about just looking at a genome file and saying, oh, well, that's kind of the genome of E. coli. That's neat. That's several million nucleotides. Cool. But it's just A, C's, G's, and T's. Now, everything's gone well at this point, so I want to read in the elements of the file, and I'm going to do that with a function called io.readAll. So I've got my IO package that I installed, and that's including this function called readAll, and it's going to take as input a field of this response variable that I have called response body. And then what it's going to return is, well, a couple things. It's going to return a slice of bytes associated with every single symbol that I see in that string. So I said there are a bunch of A, C's, G's, and T's. And this function is going to return to us a slice where the first symbol that's seen, whether it's A, C, G, or T, is the 0th element of that slice. Then element 1, then 2, then 3, then 4. So if there's several million nucleotides, we're going to have a slice of length several million, however many symbols we see in that file. And it's also going to give us an error. And so we're going to declare genome symbols as this slice of bytes and set that equal to io.readAll. And now we need to have our error message checking again. And it's okay to call this error the same because we've already used this error variable up there. And genome symbols is new, hence we're going to have a colon equals here. All right, so if that was successful, we now have a slice of symbols associated with the string, with the genome. Okay, that's cool. And then we're kind of finished with this, and I could actually just check, let's say, the number of nucleotides that we see in the genome is, well, I can get that by just accessing the length of that slice that we have. So length of genome symbols is going to give me the number of nucleotides that I have. Let's close the connection. And so I'm going to say res.body.close, and that closes that connection out. One of the things that you might also do, this is just a very brief aside, it'd be very easy to forget to close that connection. So one of the things that's nice about Go that's built in is you can, after you get this here, instead of, you're not going to be closing the connection now, you can use the built-in keyword defer, and that's going to save this to the very end of funcmain. So it's going to eventually close out the connection, but it won't close it out before you're done using it. So it'll happen at the very end of funcmain, which is useful to us. So we could try this. And I'm going to save this and compile. And it's a long compile process. And run. And here we say the number of nucleotides in, let's be more precise here, the E. coli genome is 4,639,675. Pretty good. Now, I don't necessarily want to work with just a slice of symbols. I want to work with a string. That's what FindClumps is going to take. It's going to take a string. So here's where I need to say, all right, the E. coli genome needs to be equal to converting that slice of symbols, to a string. So I'm going to have this built-in function string that we've seen before when we were working with slices of symbols, that takes a slice of symbols and converts that slice of symbols to a string. That's the E. coli genome string that we want. Let's set some values. So in a previous code along, we saw one potentially interesting value of k is equal to 9. So we might try this for different values of k, but let's try k equal to 9. That's going to be the length of a frequent word that we're interested in. Let's set L equal to 500. So we have a reasonably large region that we're looking for these substrings of length 9. And then I need a threshold that's going to say how often do I want to see this string occur. Let's set T equal to 3. Now I can say my clumps are, let's call the FindClumps function, and give it the E. coli genome, give it K, give it L, and give it T. And what we're interested in is to say, hey, I found how many clumps? Maybe it's one, maybe it's a bunch. So I'll print that to the console as well. And here is where the excitement is going to start. So I could save this, I could compile, and I can run. And we're going to have to wait. You might like to pause here if you're following along and just let this run on your computer so that you can see the conclusion that we're going to reach. We would have to wait quite a bit here. We're going to need to wait 2 or 3 minutes, I think, probably on this computer for this algorithm to finish running. So I'm not going to do that. I'm going to carry on and talk about how I could maybe make this algorithm a little bit faster. It turns out I can improve this FindClumps algorithm. And so that's what I'm going to do. I'm going to stop this process by typing Control-C in the terminal, and that will terminate the running program. And that will allow me to come back and talk about a little bit about optimization. Now, there is a Donald Knuth quote that says, premature optimization is the root of all evil. And I think that's fantastic. Fortunately, we're not optimizing prematurely. We have a nice working algorithm. We just cut it off because we weren't going to sit around here and wait for 3 minutes for it to finish. So we need to be careful with our optimizations. But I think in this particular case, we've got a working algorithm, so it's okay. And to optimize this algorithm, I am going to show you a critical insight in terms of how we can make our algorithm run faster. Every time through our loop to find all windows of text, I'm currently making a frequency table for every possible window. However, if you have one window of the text, the set of substrings that occurs in that window of the text is going to be very similar to the set of substrings that occurs in the window when you shift that window over by one symbol. You're going to lose one substring and gain one more. I could show you an example of this. So say like text is equal to banana split. I don't know if you can hear, there's like extremely loud yard work going on outside my office, but if not, that's just me. My first window, let's say, what value of L should I have? L equal to 6. My first window would be banana. And my second window, when I shift that over by one symbol, is called ananas. And you'll note they kind of line up. You see these 5 symbols are the same as these 5 symbols. So if we were looking for, say, substrings k of length, k of length 3, then this string we'd have BAN, but ANA, NAN, and ANA again, and you'd have ANA, NAN, and ANA again in the second window. And the only thing that would be different is that you would be missing this BAN, but you'd be gaining an NAS. And so if every time I slide the window, I basically throw away the frequency table, it just disappears. That's not the most optimal thing I could do. The most optimal thing I could do would be to say, wait, let's not throw away that thing. Let's just decrease the value associated with BAN by 1 since we lost the BAN. And then there's this extra substring on the end and we need to increase its value by 1. So we would need to get rid of BAN since it only occurs once in this window. And NAS is only going to occur once in this window. So we just need to add a key NAS here and assign it a value of 1. So let's go back to our FindClumps function. And I like my FindClumps function. So I'm going to copy this over, at least the function comment. I'm going to have a FindClumps faster. And it's otherwise going to do the same stuff. So I'm going to be very selectively copying here, but I'm going to have basically the same function signature, except it's going to be called FindClumps faster instead of FindClumps. It's still going to return a slice of strings. And so I'm still going to have certain parts of this code are going to be the same. I'm still going to have a slice of patterns that I'm making. It's going to start off with length 0. I still want to know the length of the text. At the end, I want to return the patterns that I have. And then it's just a matter of saying, well, what I want to change about this, I'm still going to be sliding windows. What I want to change about this is this function call. So I'll actually still keep track of which patterns I have found. So I'm still going to have this found patterns map that I'm going to use. And I'm still going to have a range over all possible windows of the text. So I'm going to copy in this for loop 2. Okay. And I need to close that for loop so that when I save it, it'll indent it appropriately. And here is where what I'm going to do is I'm going to generate. I'm going to update this a little bit. It's not going to be the exact same for loop. I'm going to generate the frequency table for the first window. Okay, so let's do that. That's the reason why is that I'd still want to call the frequency table subroutine, but only for the first window. At that point, I don't have an existing map. From that point forward, I won't need to call the subroutine ever again, but I am going to have frequency map is equal to frequency table of the first window that I have. And if I want to be very precise, I could say, well, what is the first window? It's the substring of the text starting at position 0, going up to, but not including position L, having length L. And we've actually seen that I don't need that 0 because it's going to be a prefix string of text. It's going to occur at the start, so I don't need to include that 0. I can just have text brackets :L. And so I want to form the frequency table for that first window. And I want to use the same parameter k that I'm giving that. And so now I've got the frequency table for that. Then I want to say, well, maybe I found some interesting patterns within that first window. So let's append any patterns we find to the patterns slice. And so what I'm looking for here is, let's range over all of the keys and values in the frequency map. And as I go, I'm going to be checking, is the frequency or the number of occurrences of the current string, is it at least equal to t? I don't need to check whether or not I've seen s before because there's no way I've seen s before. This is the first window. So this s can only occur one time and in this frequency map, and as a result, I'm just checking if frequency is greater than or equal to t. Once I've checked that, I'm going to say, all right, yes, I've not seen this pattern before. It occurs at least t times. So I need to say patterns. I don't know why I have brackets. Patterns equal append to patterns, the current string s that I'm looking at. And then I need to be very careful. I've now found it. So I need to set found patterns of s equal to true and flick on that light. So I would never add s to this collection of patterns again. Then I'm going to range over all possible windows of text, but I should say all remaining possible windows of text. So I don't need to start I at 0. I'm going to start I at 1. And this is going to mean that I'm going to shift the window by 1 index each time. And so I've created the frequency table for I equal to 0, and now I want to move the window over by 1 element. So I is going to now be equal to 1, and I'm going to shift it all the way, subsequently increasing it by 1 until I is equal to n minus L, which is going to be the final window. So the current window is text of I to I plus L. That's not something that I'm going to need. So I'm not going to be calling frequency table here. Instead, what I'm going to do is go back to my insight. So when I shift over from BANANA to ANANAS, I'm going to lose that BAN. And in general, I'm going to need to reduce by 1 the value associated with the key that corresponded to this initial substring of the previous window. So in order to say that, I'm going to say, well, what is the initial substring? So decrease by 1 the value associated with the first substring of length k in the preceding window. All right. Here is where the algebra could get us. This is another place throughout the course where it's probably the trickiest part of this whole thing is figuring out exactly how to express a formula for that substring. And I know what I want to call it. I want to call it old pattern because that's the thing that I want to throw out the window, I guess. Throw out and get rid of this from the frequency table that I've formed. And in this particular case, I need to look back a position. So if I'm at I equal to 1, and going back to my previous kind of made up example here, I is now here, and so I would want it to start 1 element previous. So I know that this substring that I'm getting rid of is going to start at position I minus 1, and then it needs to have length k. So it's just I minus 1 up to I minus 1 plus k. Going back to this same idea that the difference between these indices is the length that I'm interested in. If the length that I'm interested in is k, I know it needs to go from I minus 1 up to I minus 1 plus k. All I have to do is say decrease that thing. Ooh, I got caps lock on. Decrease that old pattern's number of occurrences by 1. And that's it. Except that it might have been the case, as it was in that example of banana and ananas, that was the only occurrence of that word ban. So it might have been old pattern's only occurrence, in which case, let's clean it up. Clean up the map if this was the, let's say, if the frequency of old pattern was 1. So now it doesn't occur at all. So there's no reason in maintaining it as a key. So if frequency map of the old pattern is now equal to 0, then let's get rid of it. We're going to delete from frequency map using this built-in delete function that Go gives us the key old pattern and its associated value. That's going to get rid of, I'm going to scroll back up and say, in terms of our example here, that's going to get rid of ban as a key, which is good. Now we've got keys for every other substring that occurs in the previous window. And now we're missing one, which is the last substring in my current window, which in this example was NAS. And then we need to do a little bit more algebra and say, okay, well now I've got, what are we doing? Add the pattern from the end of the current window. So I'm going to be looking at a suffix, but the algebra is going to come in and say, where is it that new pattern needs to start exactly? And we say, well, I'm going to access something of text, and the formula that I'm going to use is I plus L minus K up to, but not including position, I plus L. So if we're probably the easiest way of getting at this is not to look at this initial index of the substring, but to look at the final index. So I know I'm at position I of the string in terms of text. And I also know that I need to be going up to the end of that current window. So if I'm talking about I'm at position I, the window has total length L, then that means that I'm going up to but not including position I plus L in terms of the substring that's at the end of the window. So I'm going up to but not including position I plus L, and that tells me that part of the formula. And then the other part of the formula I can get because I know that this index minus this index needs to be K. So I can simply take whatever this is and make that minus K and set that equal to the initial index. Again, just practice with writing out formulas and getting comfortable with substring indexing. Once I've got that new pattern, that's the hard part. The easy part is saying, well, if new pattern occurs as a key, I want to set its value in the frequency map equal to 1. If it doesn't occur, or if it does occur, so it occurs 117 times already, I just want to increase those number of occurrences by 1 because I've found one more. And we have seen already in a previous code along, I can handle both of those cases in Go by just saying frequency map of new pattern plus plus, and that will handle both cases for me automatically. One more thing, I need to update the patterns that I've seen according to the current map. So I've essentially I've updated the frequency map. Yay! Because I only really did sort of two things. I hacked out the old pattern and I added in the new pattern, and I didn't have to call the subroutine at all. So I've got a new frequency map, which is good. But now I need to say, all right, well, what patterns do I find? So I will range over the frequency map, and what I'm going to do is say, is it the case that the frequency of the current string S that I'm looking at is greater than or equal to T, and I have not found S. And if both of those, which is the same if statement that I've had previously, and if both of those things are true, what do I want to do? I want to do two things. I want to append two patterns the current string S, and then I also want to make sure I flip my switch. So I'm going to say found patterns of S is equal to true. That way I'm not going to be adding duplicates. That's the same thing that we were going to do before. So I've got my FindClumps faster function written. And now the natural thing that I might want to do is call this function on the genome file that I read in previously. I might also like to time this optimized approach. So I'm going to show you, this is something that we have done previously in terms of comparing the runtimes of algorithms. So let me get that code into funcmain and run that, at least show it to you and produce this. I'm not going to actually probably run all this because it's going to take several minutes to compare the two programs, but we could do this with setting a time.now. That's going to require us to import the time package, which will be automatic when I save because I've got the Go extension. I'm going to call FindClumps of E. coli genome KLT. I'm going to have an elapsed variable that will keep track of how long it's been since I started my stopwatch. And then I'm going to print FindClumps took %s and elapsed in order to format the time correctly. And then I will say start2 is equal to time.now, and I will FindClumps faster substring KLT. I don't know why I called it substring. E. coli genome. I've got substrings on the brain. And then elapsed 2 is equal to time.since start2. And then log.printf FindClumps faster took %s and elapsed 2. And there's our code in case I want to time this. I'm really interested more in this. Okay, so I've already called this here, and this is really more what I'm interested in. So I'm going to cut this down. And I'm actually, for the purposes of this, I would encourage you to run it and compare the two algorithms. If you've got a few minutes, go get something to drink, whatever, come back and check it out. I am going to multi-line comment this stuff out because I am interested in FindClumps faster. So I'm going to call this clumps equal to FindClumps faster, and that's going to allow me to access it outside of here. So that's what I'm interested in, because the question that I'm interested in, and I'm going to go ahead and start compiling it. Ooh, I've got a compiler error. No. Line 91, cannot use s, comma, frequency, colon, equal to frequency map as value. Well, that's not good. I shouldn't have done that. Let's see what I did. Colon, equal, range. I forgot the range keyword. Okay. Let me compile. Now it compiled. And I'm going to run. All right. So that's going to be running behind the scenes. And I want to interpret the result that I'm going to get. We will see how long it took. It's also going to time it for us. I can just tell you it's going to depend on your computer, but the original FindClumps function takes 2 to 3 minutes, somewhere in there. And we want to interpret the results that we will have. But the idea being here, if we find a small number, then we know that when we scan across the genome, we might be able to say, like, if we find 3 of these substrings that occur as clumps, then that gives us a lot of information, because we would only have a very few number of regions, number of windows that we need to zoom in on. That would be great, because it would tell us there's something probably interesting going on in these small set of regions, and then we can just investigate them further. Our function took a little under 30 seconds. So on my machine, that's going to usually, it has amounted to like a 6x speed up, which is worth the time that it took us to optimize this algorithm. That's really cool. We got something that originally ran in probably about 3 minutes, and instead it's running in under a half a minute. So that's good. Optimization is great. Yay. Not as much yay is that we didn't find 3 patterns that occur as clumps. We found almost 2,000. We found 1,904 total patterns that occur as clumps. And that's different strings. There's no duplicates there. Those are different strings that are occurring surprisingly frequently, which for these parameters, that's at least 3 times in a window of length 500. You might try tweaking these parameters to see what you get. So see what happens when you set L equal to 1,000 or K equal to 7 or 8, and see how these number of clumps that you find is going to change. Also change your threshold. Get stricter. Set T to be higher so that you have to see more occurrences or fewer. Regardless of what you do, though, now that you have running code, what you're going to find is an enormous number of strings that clump when you look at a real genome. And so our idea of zooming in on maybe 2 or 3 regions of interest is not going to work. And that's maybe bad news, but it's also good news because it means that this bacterial genome is enormously rich with hidden messengers or surprisingly frequent substrings of length, in this case 9, but for all different possible lengths of short values of K. And that means that there's tons of biologically interesting stuff going on within this genome. And there are lots of regions where a protein is coming in and binding to our DNA. And the DNA has evolved to have multiple occurrences of whatever that hidden message is, that binding message, in order to ensure that mutational effects don't cause that process to break. So that is both unexciting but also thrilling, because we see that in just a statement like this, life has a lot of really cool processes going on that are using protein DNA binding. And we have an ocean of biology to study if we so wish. Play around with those parameters. See what you find. What we really want, though, is, in keeping of what the narrative of this chapter is, can we find, instead of searching through almost all 2,000 of those patterns, are we able to zoom in and solve a specific type of application? Among all those potential patterns, for example, can we find the region where the bacterial genome initiates the process of copying its DNA, initiates this DNA replication process? And rather than searching through all those patterns, we're actually going to have a much slicker, more beautiful approach for that specific application that we're going to be using to scan through the genome and do a basic level analysis, but that's also going to get us just a fantastic, amazing picture. But we're out of time for this code along. So if you want to see that beautiful approach, you're going to need to join me on the next code along. So I hope I'll see you there. Happy coding.